say a quick hello. And we have 3 exciting presentations today. The first presentation will be jointly done by Dana Miller-Cotto and Haobai Zhang. They had originally proposed to do separate presentations, but since they were working on similar areas and are collaborating, we decided to combine that presentation. So that first presentation will be a little bit longer than the other 2. Andy will be the second presenter, correct? And then I will be the third, and all of these presentations take advantage of large national data sets, so we think it's going to be really exciting. And I'll turn it over to you, Dana and Haobai.
Thanks, Nancy. I'm going to go ahead and share my screen. Can everyone see that? Okay, thanks. Hi, everyone. Like Andy mentioned, thank you so much for everyone who, it's pretty late for you. If it's early, welcome. We're pretty delighted to present our work examining executive functions and math achievement. Like Nancy said, Haobai and I were working separately on different projects that were very similar, so we decided to combine our talk, so this will be a little longer. So we'll be presenting our work on exploring the co-development of executive functions and math achievement using a cross-lag panel model with fixed effects. So as many of us have observed in our own research, it's pretty well established that math skills and executive functions are related, with recent meta-analyses demonstrating an average relationship of about 0.35 between working memory one dimension of executive functions and mathematics. Some work has also demonstrated a relationship between executive functions and various learning difficulties or disabilities, suggesting that some mathematics learning difficulties may be due to executive function challenges. However, although there's a lot of work demonstrating the relationship between executive functions and math skills, it's not entirely clear why. So really quickly, we'll talk about what are executive functions. Executive functions can be defined as our ability to regulate and control actions and cognitions. So this might include thoughts, behaviors, or how one pays attention. They're also related to numerous everyday skills, such as adding and subtracting, completing complex multi-step problem solving, and even keeping track of prices in a grocery store. If you've ever been in a grocery store and had money allocated for grocery shopping and knowing to deduct how much money and how much money is left over, that's just one real world example of where executive functions come in. And executive functions are made up of 3 dimensions. So there's 3 dimensions, and they include working memory, or our ability to store and manipulate information for later use. So that's one definition. Another definition, it could be viewed as a system of components that holds a limited amount of information temporarily in a heightened state for us to while we're doing ongoing thought processing. In terms of the second dimension, cognitive flexibility refers to our ability to switch between goals or tasks. And then inhibitory control, our ability to maintain attention and ignore distractions in pursuit of a given goal. So of these 3 dimensions, working memory is the most frequently examined in math cognition research. So a really quick Google Scholar search suggests that when you type in working memory in math, you get just over 1 million results relative to cognitive flexibility, which when you put that into Google Scholar with mathematics, you get just over 200,000 results. And then inhibitory control yields about 130,000 results. So there's been a plethora of theories for why working memory and math achievement, or achievement more generally, that have been asserted. So there's 3 subsets of theories. Cognitive filter model, which is what we refer to as a subset of theories, suggests that only a subset of information can be processed, or in other words, we have certain memory limitations. So that's explaining why math and working memory are related. The second subset of theories suggests that math and working memory are related because math and working memory share this underlying process or skill. And so we might expect that math and working memory would be highly correlated at various time points. And then the third subset of theories we refer to as a transactional model of theories. And this suggests that working memory and math are related because they not only measure our working memory doesn't only measure our ability to manipulate and attend to information in mind, but it's also our ability to retrieve information from long-term memory. So in this study, similar to prior work in this area, we set out to test these theories. And so in some earlier work that we've done, prior work suggests that the best fitting model, or the model that, when we test these models empirically, it suggests that the transactional model had the best fit to the data, likely because individuals with high working memory can offload content of working memory to their long-term memory for better efficiency. This work, however, used cross-like panel models to compare the models. And so cross-like panel models have come under scrutiny recently because this method doesn't separate out the within and between person differences when estimating the bidirectional relationships. This makes estimates really difficult to interpret. Also, as many studies in developmental science are interested in developmental change within individuals over time, it's difficult to choose the model that can appropriately disaggregate or separate out two levels of differences between person and within person in our longitudinal data. So in this study, we were interested, we examined the within person differences rather than the between person differences in the development of executive functions in math. So in other words, we wanted to know whether children who scored higher on prior math tests or math assessments relative to their own score would be or result in better executive functions later and vice versa, as opposed to whether children who score higher relative to other children would have higher executive function in later grades. And so there's a need to identify this true within person difference or variation over time with an appropriate model. So this study aimed to illustrate whether or not we could adequately separate out these two differences in a cross-like panel model with fixed effects design. We were also interested in using the cross-like panel model with fixed effects as a technique because this allows for controlling unobserved time invariant confounders, and it allows us for a clearer focus on this within person variation. We were also interested as a departure from prior work, rather than just focusing on working memory, we also wanted to see if the patterns that we observed in prior work would still hold for other aspects of executive function. So to be clear, our research questions were as follows. Is the transactional model the better fitting model still compared to the cognitive filter model when we use cross-like panel models with fixed effects? And the second research question was, does the bidirectional relationship maintain into later years? So do we see that does the strength of the relationship between working memory and math or cognitive flexibility in math remain as children get older? And so for this study, as Nancy mentioned, we used the early childhood longitudinal study of kindergarten. So this follows children from kindergarten in the United States, so from 2011 through 5th grade, which is 2015 and 2016. And so we assessed children in kindergarten to 5th grade on working memory, cognitive flexibility, and their math performance. So as you can see, it's a very large sample. And so the three assessments that we looked at, working memory, this was assessed using the numbers reverse digit span. So essentially, this is providing students, or children rather, with a string of numbers, and you ask them to provide the string, but in the reverse order. So if you ask a child, say 215 in the reverse order, they would say 512, and this string would increase until there's 4 consecutive errors, and then the task would stop. In terms of cognitive flexibility, the ECHOS-K or ECLSK data set uses the dimensional change card sorting task. So in this, the important piece about this measure is that in kindergarten and 1st grade, it uses a physical tabletop version of the DCCS. And so only accuracy data is collected for this task during kindergarten and 1st grade. But starting in 2nd grade, there's a computerized version from the NIH toolkit, the National Institute for Health toolkit in the US, which assesses performance on accuracy and reaction time. And so although they're really the same construct being measured, the scoring is different. So rather than try to combine these and make an issue of using the same scores because they're not easily comparable, we used the waves 2nd grade to 5th grade. So this was 5 waves compared to 9 waves for working memory. So for this task, children are usually given a block or 30 mixed block trials, which are all computerized. And they're asked to sort the stimulus picture based on either color or shape. So you have 2 pictures and either of them have the same shape or same color as a stimulus picture. And this appears at the bottom for children to choose based on a sorting rule. And so in each block, the sorting that appeared more often than the other was considered a dominant rule. And then reaction time on different trials with the non-dominant rules collected to figure out or detect children's performance in inhibiting the dominant response. And this should be able to shift to the non-dominant response rule. So for the DCCS, the overall DCCS scores are computed and given, in order to score it, given equal weights for accuracy and for reaction time. So for this study, we examined, again, the within-person differences rather than the between-person differences to examine the overall development for executive functions in math. We wanted to know whether children who scored higher on a prior math test relative to their own score would result better would result in better executive function and vice versa. And so to do that, we used a cross-like Pena model with fixed effects. And so the ability to control unobserved confounders in this type of model allows us to get closer to causal claims, although perfect causality would be in a different design, experimental design. And I will let Haobai take it from here.
Thanks, Dana. Sorry, I was a bit late. Can you hear me? Because, oh, cool. Because I can't hear any sound from my computer at the beginning, so I have to log in via my iPad. So anyway, thank you. And so here we showed how we apply the cross-stack Pena model with fixed effects in our context to investigate the bidirectional relationship between EF and math. So actually we started with testing a baseline model, which only contains path A and B here, the autoregressive path. And so the autoregressive coefficients would show like how stable the development of those variables are over time. And so after we got a baseline model, we added path E to test the unidirectional path from executive function to later math achievement. So we interpret this path E as how prior EF is predicting later math while controlling for the prior math. So, and similarly, we also tested the third model with adding the path F, the unidirectional path from early math to later EF. And lastly, we tested the full model with both path E and F. So it's the cross-stack Pena model we're testing, and we want to see whether the bidirectional effect existed in our model. And also different from the traditional model, and here we created a latent variable alpha, and so which is allowed to correlate with all the exogenous variables and also indicated by the endogenous variables. And this is a method proposed by Allison et al. 2017. And as Dana mentioned earlier, that the alpha here represents the fixed effect term. And the aim of adding this latent variable is to account for all the unobserved time invariant confounders in the model. So here's the equations that we use in the model. And next, please. And so the basic steps is that we fit those 4 models, and then we compare the fit of those models, gradually. And next, please. And so here are how the models were used in the ECHOS data set. So like firstly, here's the baseline model, and we have the time 1 to 9 represented 9 time points where data was collected from kindergarten to the 5th grade. And then the unidirectional path and in both directions, like in the second and third model. In the last model with bidirectional path, we tested them together. And then here is the results for the model fit for our first set of the model, which tested the relationship between working memory and math achievement. And we found that performance of the baseline model, which only contains the autoregressive path, was not that satisfactory. And so we continue to test our second model, which include the unidirectional path from working memory to math. And we found the model improved a little bit compared to the first baseline model. And then we continue to test the third model with the path on a different direction. And again, we found this model improved a little compared to the first baseline model, and the CFI is increasing a little bit, but it's still like just acceptable based on the CFI. And then we test the last model with the bidirectional path, and we found that the model fit for this one is the best among all four nested models, and which suggests that the model 4 with the bidirectional relationship, bidirectional path best capture the data. And so we think it's the optimal model which best reflect the data pattern. And so here is the path coefficients of the model. Here are the path coefficients of the model between working memory and math. And we found that we found statistically significant path coefficients from working memory to math achievement from the first time point to the last. And this suggests that the working memory at the prior time points consistently predict higher math achievement at later time points when the prior math achievement was controlled. And also the predictive power from working memory to math was, although it's statistically significant throughout the entire process, but it's in a descending order. It's in a descending trend from kindergarten to the 5th grade. And also, if you look at another direction, we found a very similar pattern that all the cross-stack coefficients are significant, which suggests that their prior math is also predicting higher working memory at later time points, but still in a descending order. And so here are the results for another pair of variables. So it's between the cognitive flexibility and also math achievement. And the fit for the baseline model, the first order autoregressive model was pretty nice. And we can see from all the model fit indicators. And after fitting the baseline model, we tested the second one with the unidirectional path from CF to the later math, and we found that the model fit improved compared to the baseline model. And then we tested the third one with the unidirectional path on the other direction. We also find that the model fit improved based on compared to the baseline model, and the fit was pretty nice. And lastly, we tested the bidirectional path. And so if you look at all four models, we found that the last one with bidirectional path has the best model fit, and also the likelihood ratio test also showed significant results, which indicate that the last model performs much better than all other three models. And again, here's the path diagrams of this this model between the math and CF. And similarly, we found that the cross-stack coefficients are all statistically significant, and they're all positive from the 2nd grade to the 5th grade, and which means that the prior math achievement is predicting a higher score in cognitive flexibility later, and this holds throughout the entire process from the 2nd grade to the 5th grade. And the same for the other direction. CF is also predicting higher math at a later time points after controlling for the prior math achievement. And so what we want to see is that we want to observe the change in the bidirectional relationship over time. So we visualize those coefficients. So we visualize those cross-stack coefficients over time for both pairs of variables. So if you look at a figure, the number on the x-axis represent the order of the period between each two neighboring time point through among all 9 time points. And the number on the y-axis represent the magnitude of the cross-like path coefficients. The figure on the left showed the relationship between the between working memory and math, and on the right is between the CF and math. And we can see clearly from the figure that the influence of math on later working memory is much larger than the effect from working memory to later math. And also similarly, we found the solid line is much higher than the dashed line for the CF and math relationship. And also we also observe a decreasing trend overall, which means the predicting power from math to later working memory is decreasing as students get older. And similarly, we found that the predicting power from working memory to later math is also decreasing as students mature. And so generally speaking, our findings are that increasing EF leads to better math achievement at later time points, and also similarly for the other direction, which means math also leads to better EF later. And also the model with bidirectional path have better model fit than all the unidirectional path, which support a reciprocal relationship between EF and math from kindergarten to 5th grade. And also, like, more importantly, in the model we're testing, we're also controlling for all the unobserved time error confounders, which makes us to get closer to making causal claim. And also, it's important to know that this relationship between math and EF are decreased as student age. And some limitations of our study. First is that even though we say we're getting closer to making causal claims, but we're not close enough, because actually we're not considering like the time varying confounders, which are unobserved. And also the latent construct EF might be better than relying on one measure of each dimension like we did in our study. So we would question, like, will we find the same results with the composite EF measures, or can we find the same results with some specific math measure? And another question we have is that, well, will we have like whether we will find the same results with a different population, such as the children with MLD, like with mathematics learning difficulties. So like from this point, we attempt to replicate our findings with the students who have mathematics learning difficulties. So we proposed 3 research questions in total, and that's our next step. So the first one is, what's the relationship between EF and math for students from K to 5th grade with MLD? So we focus on the MLD samples only, and whether that relationship will differ for students with MLD and for students without MLD. So we will do like a multiple group comparison, and whether that relationship between EF and math will change based on the different degrees of the MLD, like to what extent the severity of MLD will influence this relationship between EF and math. So I think that's it for our presentation, and thank you.
Fantastic. Thank you so much. Great presentation. And I will figure out what I'm doing. Okay, so I just wanted to make my title as long as possible. So we've called this Exploring Longitudinal Relations Between Executive Function and Math in the ACLSK, Implications of Modeling on Development of Theory and Practice. So this is, I think, a perfect follow-up talk to think about in conversation with Dana and Haobai's presentation, in part because we're using the same data, and in part because I'm looking at different approaches to modeling, which Dana and Haobai really excellently laid out the implications of using this person-level fixed effect model. So I'm really interested in the role of modeling, of statistical modeling in the development and implementation of theory. So starting with kind of this traditional adage from Kurt Lewin, there's nothing as practical as a good theory. And I'll get back to kind of why that's relevant to this talk here. So a couple of pieces of introduction that I'm going to really speed through because it was excellently laid out in the last talk. We know from decades of research at this point that EF and math are robustly correlated with one another across the lifespan. I trust that Dana was going to do a great job explaining executive function, so I'm not going to go into how I define executive function. We also know that the directional association between EF and math is uncertain. There's some evidence to suggest, like we just saw, that there's bidirectional associations, but a lot of people kind of think about one predicting the other or supporting the development of the other skill. And it remains to be seen whether there's actually a causal relationship between these two sets of skills. There's been extensive kind of looking at far transfer of executive function trainings on math skills, math training on executive function, and really seeing mixed effects of those. So I kind of come at this from the more traditional idea that executive function supports math skill development. If you have higher levels of if you have higher levels of executive function skills, you're going to develop mathematical skills at a faster rate. And this is really built off kind of traditional information processing theories like that of Robbie Case, where we have these core capacities like executive function that help children to develop further skills that are more academically relevant or academically testable, we might say. But there have been a lot of other alternative models of the relations between executive function and math. So just like that last presentation we saw, there's these bidirectional models. We see this kind of either common construct model or this idea that it might be the multiple skills rather than the structure of EF itself that predicts math. Or we have kind of extensions of latent growth curve modeling and autoregressive path modeling, where we have, this is from a recent, oh, I didn't cite that, that's a problem. We have a relatively recent study from Willoughby et al. Looking at a parallel process growth model and controlling for structured residuals to look at both between and within person changes in math and executive function skills over time. So what I'm doing in this talk is asking the questions, does the way that we think about and model and statistically analyze the relations, the dynamic relations between executive function and math, because most of what we've done in the past is cross-sectional, it's not necessarily taking into account the dynamic, the inherently dynamic nature of these two skills. Does that affect the theoretical conclusions we can draw? And based on the different ways of modeling the relations between EF and math, is there support for one directional hypothesis over another? This is using the same set of data that were talked about in the last study, with the one amendment that I'm using only kids who did not have any kind of IEP, or who did not at any point enter a grade that they were not meant to be in, either redshirting, being in kindergarten for a second time, skipping grades, or being held back. So that limited my sample size to about 12,000 kids instead of the 18,000 some odd kids who are in the full sample. I'm going to jump over this because, again, it's been talked about, and most of us know the structure of the ECLSK. And so really I'm focusing on the early math measures and the numbers reversed. So I say that I'm looking at executive function. I recognize here that I'm looking at only one component of executive function, that being working memory. I'm not looking at the DCCS in here. I'm happy to get into other conversations about ways of modeling executive function and measuring executive function and trying to determine effective measures of executive function, but we're going to leave that behind. So I took a few different approaches to looking at these data. The first was a traditional autoregressive cross-lagged panel model. So in this, we're controlling for the prior level of skill, this autoregressive path, where we assume that there's going to be a high degree of correlation between former math and future math. So math in the fall of kindergarten is going to be highly related to math in the spring of kindergarten. We expect that's going to be less so, but still true for working memory or executive function more broadly, because there's a lower degree of stability in executive function or measurement thereof, whereas math is typically measured pretty stably over time. So looking at this, I didn't include the model estimates or the parameter estimates. I'm just looking at, this is really echoing what Dana and Haobai just talked about, that we see this cross-lagged model where each skill is predicted by the former alternate skill, which is to say that later executive function is predicted by earlier math, just as later math is predicted by earlier executive function. So this is supporting the kind of bidirectional idea of the relations between EF and math. But there's some problems with the autoregressive panel model, as Dana talked about in the previous talk. So I took a couple of different approaches as well. One that I'm not going to talk about extensively because we have relatively limited time is I looked at single parameter growth models, looking at, does the starting point of math predict growth in EF? And does the starting point of EF, which is to say the fall of kindergarten, predict growth in math over time? And the answer to those is yes, which is to say that, again, the point at which children start their kindergarten career in mathematical or executive function skill predicts not only the starting point of the other skill, but also the rate at which they develop the other skill. So complicating that a little bit, I estimated a parallel process growth model looking at both the starting point and the rate of change. These were unstructured slope models rather than assuming some kind of linear slope. A lot of prior work has shown that math especially develops in a quadratic function, but that's not an equal quadratic function over time. It starts to slow around the time that kids enter start to enter second grade. So here we're regressing the slope functions, the rate of change on the starting point of the alternate skill. That is to say that the math skill or the rate of change in math skill was regressed on the starting point of executive function, and at the same time, executive function rate of change was regressed on the beginning point of math. We also allow for correlations within skill and across skill, and we find that these are all significant pathways. We see that the starting point of executive function predicts the rate of change of math. The starting point of math predicts the rate of change of executive function, and that these are correlated both when children enter kindergarten, and the rate of change is correlated such that children who develop math at a faster rate also are more likely to develop executive function at a faster rate. So again, this doesn't tell us a lot about the directional association, but that there is some correlation in the degree of change over time. So then, following up on some of the work done by Willoughby et al., I looked at this same model, same idea of the starting point and change, predicting the starting point and change of math and executive function. But I also include these structured residual variables, so or parameters. So essentially what we can think about in looking at these models is that the latent functions, the executive function, intercept and slope, and the math intercept and slope are kind of like between person change. This is the aggregate level of, do we see that there is a developmental trajectory whereby slopes on average are correlated with one another. And then this within, these structured residuals and the cross-lagged estimates among the structured residuals are more of a within person estimate. So for a given person, over and above the the group level co-development of executive function and math, is there anything where we can say that math predicts development of executive function within person, and that executive function predicts development of math within person? So this is just kind of combining the last two approaches for a more conservative estimate of the relations between EF and math. So echoing the last slide with the parallel process growth model, we do see that these associations at the group level remain significant. We also see that the autoregressive pathways are significant, that within person controlling for group level means that executive function is relatively stable and math is relatively stable. We also see a within person correlation where EF and math are correlated at each time point. What's perhaps the most interesting, or the most interesting to me, is this one directional pathway where particularly early, so again, EF1 and EF2 are fall and spring kindergarten, not grade 1 and grade 2. We see that early executive function predicts the following level of math within person, but not the other way around. So given that we have very limited time, I'm just going to end quickly with conclusions and implications. This is very early level work, and I'm thrilled to hear anyone's feedback about where this could go. But what I'm finding here is that the ways in which we model the relations between EF and math, or any two dynamic constructs, can substantially change the conclusions that we draw for theory. I can make my paper say that there's bidirectional relations between EF and math, or I can make my paper say that there is a unidirectional association where within person EF predicts math, and neither is wrong. It just depends on which modeling approach I'm using. And this might in turn affect theories of practice. So if we don't see any association in later grades where executive function predicts math, and this again is just kindergarten, first and second grade, this is a very early pass. But if we see that extending this same model where we didn't see these later associations, particularly toward the end of second grade, and this here might be something about what's happening over summers. I'm not entirely sure. I have to dig a little bit more deeply into that. But if we see that something about executive function development in schools isn't predicting or supporting the development of math skills, then that might not be an area of practice that we want to focus on. We might not want to develop executive function interventions at later grades. It might make more sense to focus on earlier grades, if at all. And importantly for my theoretical approach, there seems to be some within individual directional associations where EF supports math skills. But on the whole, we still see that EF and math and their development are correlated across the sample. So as I opened with a quote, I want to close with a quote, which is that in theory, there's no practice between theory and practice, but in practice there is. So it really matters for our theory development how we implement this practice. So thank you all so much. I'm happy to turn this over to you, Lynn, and I am excited to continue the conversation.
Okay, hi everyone. Can you see my screen? Okay, I shall start. So thank you very much, everyone, for being here. I'm very happy to be part of this symposium. So for this talk, we are using data that we've collected from a longitudinal study that we did in Singapore called the Singapore Kindergarten Impact Project. So in short, we call it SKIP. And the aim of this project was really to look at how children's preschool experiences impact on their developmental outcomes. So we followed children from the ages of 5 until 7, where they started formal schooling here in Singapore in primary 1. So in this talk today, we're using this data set to look at a slightly different question compared to the other 2 talks earlier. So basically, we're trying to look more deeply into this achievement gap that we see between high and low SES children, and trying to see whether measures of executive functioning and self-regulation may help to explain these links between SES and math achievement. So it's also slightly different from what was described in the abstract, but I thought I made this change because I thought this would be a slightly more interesting talk. Okay, so to start off, our starting point for this study really is this very well-known achievement gap that we see in children from high and low SES backgrounds. Findings from both individual studies as well as meta-analyses have shown us that there is an achievement gap. And for example, children from low-income families tend to start kindergarten behind their middle-income peers in early math. And these initial math deficits also contribute to slower growth in math from the 1st to the 3rd grade. And these are studies that have been done in the US. And so therefore, we think that it's important to understand these underpinning mechanisms that drive this link between SES and achievement so that we can get further insights on how we can support children from low SES backgrounds with the ultimate aim of reducing the achievement gap. So we looked into the role of domain general factors and we focus on 2 here. The first is executive functioning, which Dana and Andrew have talked about in great detail, so I won't talk more about that. The only thing I would mention is that for measures of EF, we typically assess under very controlled conditions, and it's also less context dependent. So think about the TCCS or the numbers reverse kind of task. It's either assessed using paper and pencil measures or in a computerized mode. The other domain general factor we're interested in is self-regulation, which we define as a very broad construct that refers to one's ability to use higher order cognitive skills, which include EF, within very complex and demanding environments. So within the context of a classroom, we are looking at whether children can remember multi-step rules, can they ignore distractions and persist on difficult challenges in the classroom. And so in contrast to EF, self-regulation skills are typically assessed in more naturalistic settings. For example, using either parent or teacher reports of how children behave. But at the same time, there are also direct child-administered tasks that are used to assess self-regulation. And so what do we currently know about the relations between these different constructs? So first of all, we know SES is predictive of children's executive functioning skills as well as their self-regulation skills. And we also know that both self-regulation and executive functioning skills predict children's math achievement. There's also some studies showing that different ways of assessing EF, either using direct assessments or using teacher reports, provide independent predictions to children's math skills. However, we know very little or slightly little about how these different measures of domain general skills, self-regulation and EF, how do they account for the SES achievement gap in math? So could it be that self-regulation and both EF uniquely account for some of these differences, or when you put both types of factors in the model, only one emerges as a significant predictor? So I haven't found many studies that have looked at this issue, except for a very recent study by Findus, which incidentally uses the ECLS cohort data. They've examined this question, and what they found was that both self-regulation and executive functioning accounted for initial SES-related disparities in math at K1, so at the start of kindergarten. However, when they looked at these relations at grade 3, only executive functioning continued to explain achievement gaps. And then another study has found that when we look at SES and self-regulation, executive functioning skills and math, the relations that you find may depend on the context that you're in. So another study by Ellefson and colleagues compared children from Hong Kong and the UK, and they found that the mediator that emerged significant was different in these two different contexts. And so based on these findings, we thought that it would be interesting to look at these questions within the Singapore context. And so our aims were mainly to clarify the contributions of executive functions and self-regulation skills to the SES achievement gap in math as children enter the formal education here in Singapore. And we also wanted to see whether different ways of assessing self-regulation would provide a unique perspective of how children apply their skills. So we compare both direct measures and teacher ratings of self-regulation. So again, as I talked about earlier, our sample was obtained from SKIP, which was a longitudinal study. And within this broader study, we followed children from their first year of kindergarten, or K1 at age 5, through the second year of kindergarten and their first year of primary school at age 7. So primary 1 here reflects the first year of formal schooling here in Singapore. So our participants were about 980 children. They were about just close to 5 years of age at the entry to this study, and we had about equal proportion of boys and girls in this study. So the key measures that we used in this study were taken from 3 different time points, K1, K2, and P1. So for the SES variable, we used data that we collected at K1, which included parent reports of their household income as well as their highest education levels. And then we derived a composite variable that includes these 3 variables to assess children's SES. So higher scores on this composite reflects higher SES. And then for measures of self-regulation and executive functioning skills, we used data that we collected at K2, which is their second year of kindergarten. So for teacher-rated self-regulation, we used the learning-related social skills subscale from the child behavior rating scale. So teachers would rate children on a scale of 1 to 5 on different items describing whether children are attentive in a classroom and whether they are able to persist on challenges within the classroom setting. And then we also had a child-assessed measure of self-regulation, and this is the head, toes, knees, shoulders task. And lastly, we had a battery of tasks assessing executive functioning skills in children. So this was a composite of 7 tasks, which cover the 3 EF skills of inhibition, cognitive flexibility, as well as working memory. So examples are like the flanker task, numbers reversed, as well as the DCCS that we talked about earlier. And again, we derived a composite of these 7 tasks. So we have sort of an observed EF composite that involves all of these 3 different skills. And then for math achievement at primary 1, we use the test of early math ability, which is a standardized measure of math achievement. This assesses children's skills in both informal and formal math knowledge. So here's our analytic plan. We used a path analysis to look at the relations between these different constructs. So basically, we're looking at the 3 different measures of self-regulation and EF as mediators between SES and math achievement. But I would use mediators in a very loose sense here because although this was a longitudinal design, I don't think we can talk about mediation specifically, but probably more in terms of indirect effects. So each of these self-regulation measures predicted math, and we also specify an indirect path between SES and math achievement for each of these self-regulation executive functioning measures. We also included some additional paths, which I didn't include in the model just for simplicity. But basically, for the math achievement measure at P1, we also controlled for their math at K1 entry, their age, as well as the time elapsed between the K1 and P1 assessments. We also modeled each mediator here to be predicted by their nonverbal reasoning skills as well as their age at the K2 assessment. And SES was allowed to correlate with nonverbal reasoning, and we allowed correlated residuals amongst all the three mediating variables here. So some bivariate correlations to share here on this screen. So the first thing I would highlight is all the three measures of self-regulation and EF were positively correlated, as you can see in these pink squares here. And then each of the self-regulation and EF measures also significantly predicted math at primary 1, as shown in the green boxes. And we also find SES is significantly related to all of these variables, EF as well as math, as shown in the blue boxes. So going on to the path analysis findings. So all the paths on this model here was statistically significant. SES had a direct link on math achievement at primary 1, and each of the measures of self-regulation and EF also significantly predicted math, and the model fit was acceptable, and the table at the bottom here shows the indirect effect for each of the self-regulation and EF measures that we had. And so what you can see here is that there were indirect effects involving all three measures of EF and self-regulation, and the strongest one was the path through teacher-rated self-regulation, which we used the learning-related social skills. So what are the implications of our findings here? So first of all, our findings suggest that both executive functioning and self-regulation are distinct constructs that could potentially mediate this SES achievement gap in mathematics. And this is interesting to us because we use different ways of assessing EF and self-regulation. And it seems to show that different ways of assessing EF and self-regulation does have an important role to play and tells us a slightly different story. The second point is that direct and teacher-rated measures of self-regulation also capture different contextual applications of self-regulation skills. So whereas direct measures tell us the skills that a child has, the teacher-rated measure tells us a little bit more about how children apply these skills within the context of classroom. And we also found that each measure uniquely predicts children's math achievement at primary 1, but it seems that it's children's ability to self-regulate their behavior in the classroom as observed by their teachers provided the strongest indirect effect. And so from a practical perspective, our results seem to suggest that in order to reduce the SES disparities in math achievement, it might be important to enhance children's executive functioning as well as their self-regulation skills, both in structured as well as unstructured contexts. And that's the end of my talk. Thank you.
Well, that might be our best timed symposium yet, despite the message that I got from Nancy about 5 minutes in saying that she wasn't sure if we were going to be able to do it on time. So great job. If anyone has any questions, I'm sure that all the presenters would be happy to stick around for a couple more minutes. Otherwise, let's keep the conversation going, and we will look forward to seeing you for our next symposium next Thursday. Nope, sorry, we have a workshop next Thursday, don't we? Thanks, everybody. Have a great day, have a great night, have a great morning.